Lecture 6, Lie derivative, definition and application. This is the space, that's a manifold, and this is the tangent vector space, TP M3, that's point P. This is point Q, and this is the tangent vector at point Q. Now remember that point P is phi of 0, okay? This is the parametrized by a time t. And also point Q is phi of eta. You see that eta is a small increment, is a real increment, is a teeny increment, which eta is equal tq, as you pointed out before. So this is a push forward from this space to that one. You see, this is the operator. This is d phi of minus eta. Minus eta brings push forward from Q to P, as is written right here. So this is important because this brings the vector yq to the point P, from Q to P. Then I denote as y tilde of P. This is a push forward. This operator here is a push forward that take the vector yq to the point P, from Q to P. This g of P, this is a scalar, is a function, okay? And yp, you see, this applied to iq. You see this y tilde is a point P. Consider G the Cartesian coordinates xj. Remember that coordinates are functions, you see? So this is a functions where j, for instance, if the manifold is three-dimensional, j is equal 1, 2, or 3. You see, this is a free index. This belongs to the manifold. Attention now. G, you see, is a function that belongs to the manifold. In this case, M3. Could be M4, see, M5, and so on. The push forward, by definition, you see, as I pointed out here, is d phi of minus eta. You see, minus eta is because eta is equal tq, which is greater than 0. So minus eta comes from Q to P. Eta goes to P to Q. You see, that's why minus eta here. Acting on yq, this leads to the vectors, the space, the vector yp, y tilde at P. Now the pullback, you see, that's opposite, okay? Now, this is important. Pushward acts on vectors. Pullback acts on covector or dual vector. But let's consider GP, and the pullback will act on this scalar, okay? This is a function, okay? In general, pullback acts on the covector, see? But this is acting on this function here with the G, you see, composed with phi. Now, GP, okay, P, attention, P belongs to this case, to the manifold, okay? It's important here but that the coordinates, okay, belongs to the manifold. That's important here. So the pullback here, GP, is xj. You see, these are coordinates at P. The pullback, okay, this take the coordinates here at P and leads to the point Q. That's a pullback. Pullback is from P to Q. Push forward from Q to P. That's important to emphasize. This adjoint identity or adjoint operator we'll not use on this lecture because we will apply the definition of Lie derivative directly, okay, using this formulation over here. This is a definition, you see. That's a limit what eta goes to 0, okay, that the push forward, okay, this over here, you see, is the same of y tilde at P. You see, don't forget that. You see, minus yp divided by eta. You see. Now, what means the Lie derivative? It measures the infinitesimal change in y under the flow generated by x, capital X, tangent vector, evaluate at point P. That's what is the Lie derivative? What means the Lie derivative physically? Okay, this means that. Okay, this is a change in the vector y. Okay, and when you have the flow is generated by the tangent vector x. See, so that's written over here. Now we will see an application using this definition. We will see later, when we use the adjoint identity, that there is a formula, okay, involve the Lie bracket, but this we will derive later, okay, also in this the Lie derivative. So I will apply this definition in a special case of the manifold, which is the sphere. Okay, this is a spherical coordinates r, theta, and phi. Remember, r is the radius, theta here, okay, is the polar coordinates. You see, and phi is azimuthal. Okay, theta, okay, goes to 0 to pi, 0 to pi, and phi from 0 to 2 pi, okay, 2 pi, that's around. Theta is 0 to pi, is a co-latitude. Theta is a co-latitude, you see. Now, then here, consider the curve parameterized by time t at points P and Q. P is phi of 0 and Q is phi of eta, with eta is tq minus tp. You see, this here, you see this figure here, this is, that's right here, tp, and this one, this point here is tq. So eta, you see, is just tq minus tp, you see, which I wrote over here. You see, obviously tq is greater than 0, okay? Eta is greater than 0. Now, coordinate chart, P, okay, sits at xi at 0, and Q in this case is at xi of eta, where I, 1, 2, 3 in this case of the three-dimensional manifold is a free index. Now we define the tangent vector along T parametrization. xp is xi dt. This is the basis vector, okay, at p. Likewise, x, the tangent vector x at point q is dxi dt. Also, this is a base vector at q. Now, tangent vector along lambda parametrization. See, you see this figure over here. This curve over here, this curve gamma, is parametrized by time. This curve I'll call here, in this case, let's call gamma prime. Okay, gamma prime is parametrized by lambda. You see? Likewise, this is gamma double prime. You see, they are parametrized by this case, the time lambda. Okay? X is parametrized by the time t, as I pointed out over here. So this I call accelerated curve. Yp, the definition, you see, this is dxi by d lambda, not dt, at point p. Yq is a tangent vector of this curve parametrized by lambda, is dxi or dt. This is a basis vector. Now this figure here explains exactly what I wrote over there. You see, this is a parametrized by lambda, parametrized by lambda. And this curve here is parametrized by, in this case, by time t. So, then on the lecture 7, I will continue, okay, just to apply the definition of the Lie derivative to the spherical coordinates.